Hi everyone, happy holiday. And today let's solve the weekly contest median question, Jump Game 6. The question statement, so we're given an integer array nums and an integer k, and we are initially standing at index 0. And in one move, we're able to jump at most k steps forward, but cannot jump outside the array boundary. So that means we can jump from index I to any index in a range of I plus 1 to minimum of n minus 1 and I plus k inclusive. And we want to reach the last index of the array, and we have a score that is the sum of all elements we have visited in the array. And we have to return the maximum score we can get. So for example 1, starting from the first element 1, we can jump forming the subsequence 1, -1, 4, and 3. So the maximum score we can get is 7. And for example 2, the jump will be 10, 4, and 3. So the sum will be 17. And for example 3, the maximum score we can get is 0. And the data constraint, the length of the nums array can go up to 10 to the power of 5. So if you have worked on other jump game problems, then you will know that the approach to solve this kind of questions is dynamic programming. And here the DP array is the maximum score we can get at index I. And the initial value of the DP array is the first element in the nums array. And DP transition, since we can jump k steps forward in the nums array, the maximum score we can get at the current element will be the maximum of nums I plus dp I minus 1 or dp I minus 2 all the way back to dp I minus k. So as you can see, the key part is to keep track of the maximum of the DP array in a sliding window. So the data structure we can use is a DAC data structure, which is double-ended queue. And for DAC data structure, we're able to pop elements from the left or from the right. We will pop elements from the left to make sure that all elements in the DAC stays within the sliding window. And we will pop elements from the right to keep track of the potential maximum in the sliding window. And this technique is the same as solving question 239, sliding window maximum. So make sure that you check out this question as well. Now let's look at the code. Okay, and first create and initialize the DP array. And then create a DAC queue, and we will put a tuple of the current element num and its index into the queue. And next, iterate through the nums array. First calculate dpi, which is nums I plus q00. And next, we only want to keep potential maximum, sliding window maximum, in queue. So if dpi is bigger than the last element in queue, then we will pop it out from the right. And then append dpi and its index I into the queue from the right. And next is to check if the first element is still within the sliding window. So this if condition, if I minus k is equal to q01, this means that this element, it will be leaving the sliding window. So we will pop it out from the left. And finally return the last element in the DP array. Now let's see the code in action. Here we will be looking at example 2. And in this example, k, which is the width of the sliding window, is 3. And the output will be 17. So initially, dp0 will be 10, which is the first element in the nums array. and we will push the first element and its index 0 into Q. And at index 1, dp1 is -5 plus the first element in Q, which is 10, so it will be 5. And next is to push the dp value 5 and its index 1 into Q. And since 5 is smaller than the elements in Q, 10, so this element will not be popped out. And at index 2, calculate dp2, which is -2 plus 10, which is equal to 8. And then push 8, 2 into Q. You can see that 8 is bigger than 5, which means that 5 has no potential to become the sliding window maximum. So we will just pop it out from the right. And here you can notice that the current sliding window maximum, which is the maximum of dp I-1, I-2, all the way back to dp I-k, will always be the first element in Q. So that is the main reason why we are updating dpi by adding nums I and the first element in Q. And following the same process, at index 3, dp3 is 4 plus 10, which is 14. And then push 14, 3 into Q. And now 14 is bigger than either 8 or 10. So we will pop 10 and 8 both from the Q. And at index 4, dp4 is 14 as well. And we will push 14, 4 into Q. And here you can also notice that since the width of the sliding window is 3, so the left pointer, which is the left boundary of the sliding window, will be now pointing to index 1. And finally, the last element is 3. So dp5 is 14 plus 3, which is 17. And 17 is bigger than 14, so these two elements will be popped out from Q. So the result, the final output, is the last element in dp, which is dp5, is 17. And this will conclude the algorithm. Finally, let's review. So the algorithm we use to solve these questions is dynamic programming. And the meaning of the dp array is the maximum score we can get at each index I. And the key data structure we use in this question is a DAQ, which is a double-ended queue. And this key data structure, this technique, is what we use in solving the related question 239, the sliding window maximum. So be sure to check out this question as well. And the time and space complexity of this approach is both linear, big O of n. Because we are looping through the array once, and we are maintaining a DAQ to keep track of a sliding window maximum. And that will be all for today. Thanks for watching. If you like this video, please give it a like and subscribe to my channel, and I will see you in the next one.